Hello, welcome back. We are going to take a look this time at atoms. Atoms are in chapter 4. And we just need to think a little bit about how do we know so much about something that's so little. And we live in a time where we're really lucky to have some great electron scanning microscopes and some great tools to look at this, but that hasn't always been the case. So hopefully by now you've taken a look at, or you will soon take a look at, the scientists that have come before us that have helped us look at all the steps that have helped us discover electrons, protons, neutrons, and you live in an exciting time when there's even more being discovered all the time. So let's take a look at atoms. Atoms are so tiny. The average atom is about 300th of a millimeter, or of a centimeter. If you look at a penny, it has 2 times 10 to the 22nd atoms. That is a huge amount of atoms for a little tiny penny. I set that out in number form, and if you can look, you can see that it has 1, 2, 3, 4, 5, 6, 7 sets of zeros. That's how many atoms in just one penny. When we're looking at atoms, we're really looking at the subatomic particles. Subatomic is a way to say the parts that are inside of an atom. Sub, under or in, and atomic is about an atom. There are many different kinds of particles inside of an atom. Many have been discovered or proven in the last 50 years. And if you take a look at the link that I have, Wikipedia has a complete list of subatomic particles. We're really only going to look at 3. If you are interested in subatomic particles, you're living in a time when the Large Hadron Collider at CERN, the LHC, is leading research and looking for all kinds of new parts of the atom. They actually just recently have confirmed the Higgs boson, and they've been looking for antimatter and dark matter. But we're going to stick with just the basics this year. Subatomic particles, we're going to start by looking inside the nucleus. If you think back to what you remember about cells, the nucleus was inside of the cell and had all kinds of the major parts, the control center. In the atom, the nucleus is at the center again, but it's a little bit different this time. It isn't the control center, but it is where the protons and the neutrons hang out. The protons are positively charged subatomic particles in the cell. Neutrons are in the middle and they have no charge. They're roughly equivalent in size. They both have the mass of approximately 1 mass unit. Talking more about protons. Little joke is, think like a proton, always be positive. Each element has a specific number of protons in the nucleus. If it has a different number, then it's a different element. Gold must have 79. Hydrogen has to have 1. Helium has to have 2. When you look at the periodic table, those numbers that are on there tell you how many protons it is. The reason we can't create gold is we don't know how to add more protons to the nucleus, and so gold always has 79. It's the way it exists in nature. If it had 80, it wouldn't be gold anymore. If we're looking at subatomic particles outside the nucleus, we're looking at electrons. They're negatively charged. They're so tiny, they don't really have any mass, and they're in what's called the Electron Cloud. They're negative. They don't want to be next to each other. It's like 2 ends of a negative magnet, and so they're always pushing each other apart, and they move very fast. And so when we look at them under a very powerful microscope, we see just this cloud of electrons. And that's where they could be at any given moment, or that's where they were at that moment when a picture was taken one time. If we're looking at the cloud, different levels or different distances from the nucleus, which is the red, are different energy levels. And so when we get into Bohr diagrams, we're going to start talking more about energy levels, and we're going to start talking about how those energy levels affect how things bond together. I thought I had a slide on neutrons, but I don't see it. So neutrons are, they're in the middle and they don't have a charge. They have no charge at all. They're not positive, they're not negative, but they are the nucleus and they do have mass. And so they do add to the total mass of the atom. An atom wants to be electrically neutral. and have no charge for the whole thing. And in order to do that, the number of protons has to be equal to the number of electrons. And so in a perfect world, you want your plus magnets to balance out your minus magnets, and so you get this equal, and the atom would like to be equal. And so when we talk about atoms, we talk about having the same number of electrons as we have protons. Same slide, same information, just a couple different ways of showing that. If you look at the one at the bottom, you'll see that it has 1, 2, 3, 4, 5, 6, 7 protons, and 1, 2, 3, 4, 5, 6, 7 electrons, 2 close in and 5 farther out. Again, we'll talk about that more when we talk about the Bohr diagram. You'll also see that it has 1, 2, 3, 4, 5, 6, 7 neutrons. It is not uncommon to have the same number of neutrons as protons, but it is not required to have the same number. Likewise, the diagram to the right is what we consider a little bit more classic. We're going to call this a Bohr diagram. You'll notice again they put 2 electrons on this first ring, and there are 5 electrons on the second ring. This atom has in total 7 protons and 7 electrons. So, if all the parts of an atom are identical, what makes the different atoms different? And as we talked about earlier, the number of protons in the nucleus is a huge factor. Each type of atom has a different number of protons, and each atom also has a different number of electrons, because there need to be the same amount of protons as electrons if the atom is going to be neutral. So if hydrogen has 1 proton, hydrogen is naturally going to have 1 electron. We're going to get into some exceptions to that later, but for now let's stick with that rule. So as you're taking a look at a periodic table of elements, you're going to see that it is covered in numbers. You're going to find periodic tables in many different locations. You're going to find a periodic table in any science classroom. You'll often find them in the back of a science book, sometimes in the back of your planner, and if you search periodic table, you'll find all kinds of apps and websites full of them, because they are the parts that make everything around you. So when you take a look, you're going to see an atomic number. That's the number of protons in the nucleus of that atom. And as we keep discussing, every atom, every element has its own specific number of protons. It's like its fingerprint, and so that atomic number is going to be the number of protons that are in that nucleus of that atom. There's also a mass number, which is the sum of protons and neutrons in the atom, and then there's going to be a more specific number, the atomic mass. That's the average mass of all of the isotopes of an atom. An isotope is just a fancy way of saying a version. An isotope could be a different version of the same element. So it could be a gold element that has more or fewer neutrons. The number is going to be a decimal because it's going to show you what the average is for all of the known isotopes out there. For instance, if we take a look at sodium, this is what we'll find out. Sodium is abbreviated with a capital N and a lowercase a. That's the symbol we use for sodium in science. The atomic number is 11. That tells us that there are 11 protons in every sodium element. If that element is balanced, it's also going to have 11 electrons, 1 electron for each proton. This periodic table is showing you the atomic mass. The unit for atomic mass is the atomic mass unit. It is 22.99. What that tells us is that sometimes sodium can be found with 11 neutrons, making it a mass of 22, but more often it's found with 12 neutrons, making it a mass of 23. If we want to find out how many neutrons there are, we always have to find the atomic mass, and that is the atomic mass rounded to the nearest whole number using good rounding rules, and then subtract the number of protons, and that will give us the number of neutrons. So in this case, 22.99 rounds to 23. 23 minus 11 protons, because each proton has 1 mass unit, will tell us that most versions of sodium out there have 12 neutrons, and the 11 plus the 12 come up with 23 AMU, atomic mass units. Always make sure that you round that atomic mass before you subtract. Remember, a 5 rounds up and a 4 rounds down. So let's practice a little bit. If you get a table like this, you should be able to, knowing the name or the atomic number, be able to figure out all the other parts of this. Or if you know the protons, you don't need to know the atomic number because they'll be the same. So let's start with lithium. Lithium is abbreviated with capital L, lowercase I. It's got an atomic number of 3, which tells us that the number of protons is also 3. It's got a number, I hate when it does that. It's got a mass number of 7 because 6.941 rounds up to 7. Using that, we can calculate that the number of neutrons most often is going to be 7 minus 3, which is 4. Number of electrons has to equal the number of protons, so if the protons equal the atomic number, then the atomic number, the number of protons, and the number of electrons are all 3. Take a minute, fill out the rest of this table. See if you can figure them all out. You can pause this video while you jot this down. Is this what you came up with when you took a look at your periodic table and these small number of elements? If it is, then you're on the right track. If not, then let's check in together and find out what you're missing. We also need to find out what an ion is. An ion has a charge. They have the same number of protons that any other element would have, but they have a different number of electrons. If it has more protons, it has a positive charge. If it has fewer, it has a negative charge. So if it has 2 protons and 1 electron, it's still a helium, but it has a negative, or it has a net positive charge because it has 2 positive charges and 1 negative charge, and 2 minus 1 is plus 1. You can also get helium that has 2 protons and 3 electrons. This would give it a negative 1 charge because plus 2 minus 3 is negative 1. Ions are how things bond together, and ions are how electricity is made. We need our nature to have these different numbers of electrons in order for things to interact with each other. So we will learn not only how the atoms work and the different isotopes of the atoms, but we'll learn this year about how the ions interact together too. So when we look back, isotopes are atoms of the same kind but have different numbers of neutrons. Isotopes have the same characteristics as the other atoms, but they change in mass simply because of the changing number of neutrons. Going back to lithium that we used in the previous example, lithium is always going to be atomic number 3, as shown in this bottom corner. But you can find lithium out in nature that has 6, 7, or 8 as a mass. That is because it can either have 3 neutrons, 6 minus 3 is 3. It could have 4 neutrons, 7 minus 3 is 4, 1, 2, 3, 4. Or it could even have 5 neutrons, 8 minus 3 is 5, 1, 2, 3, 4, 5. All the while it still has these 3 protons, and if it's a balanced element, it still has these 3 electrons. We're going to pause here, and we're going to pick up next time with forces of an atom.